Awesome. Okay, and with that, it is my great pleasure to introduce the very first, the first speaker, Krishna Shankaranarayan from IIT Bombay. Krishna works in the area of program analysis and verification, and today she is going to talk about verification of concurrent programs under release acquired consistency. And on to you, Krishna, please.
Okay, thank you so much for the invitation and also for a nice introduction. So the talk is for 1 hour, right? Just to clarify.
Yes, that's
All right.
right.
All right. Okay. Yeah. Okay, so I guess I'll get started by talking about concurrency itself, even before I get into release acquired. So just a motivation for concurrency, I guess the just motivation is that concurrent systems are everywhere. So when I say everywhere, what I mean is that if you look at all across levels of system design, you will see concurrency. For instance, if you start at the lowest level of the system design, which is say at the level of the chips, and if you look at any of the leading manufacturers of processors like Intel or ARM or Power, IBM Power, invariably these are all multi-core architectures, which tells us that we have concurrency at the lowest level of system design. Okay, now let's move forward and look at the highest level, potentially highest level of system design, which is the distributed databases. So here, if we look at, let's say, the databases of Facebook or Amazon, so what they have is what are called the geo-replicated systems because the servers are distributed across the world. And these are necessary to kind of give a consistent view of the system. So, for example, sitting in Mumbai, if let's say I like the Facebook post of a friend, or if I just post something, then somebody in Auckland should see it simultaneously, right? So this is how the concurrency works at the highest level in distributed databases. But now, if we look at the implementation of any modern programming languages like C++ or Java, so here also we see parallelism and concurrency at the inside the programming languages. So this is why we have things like threads or locks or let's say release accesses or acquire accesses and so on and so forth. So this also immediately leads into the topic of today's talk, which is I will begin with weak memory even before we talk about release acquire. So weak memory models at a very high level, I'll just describe them as something that provides sound semantics for high performance concurrency. So there is this trade-off between, easy programmability on one hand and high performance on the other hand. And what is known is that the traditional model for concurrent systems, which is sequential consistency, is very easy to program and it has a standard interleaving semantics. But its performance is quite difficult because it has a lot of synchronizability going on. So usually it is very expensive. Now, on the other end, right, the trade-off between programmability and high performance, on the other end, we have so-called weak memory models or relaxed models, where the performance is very good. However, they are barely synchronizable. So what I'm talking today and what you see in between, okay, is the release acquire semantics, which seems to balance both of these quite nicely. And of course, I'll talk a bit more about that. For now, release acquire is a very well-behaved fragment of C11. So what exactly is C11, right? So again, we can think of the C11 memory model to be divided into two parts. So one hand, we have what are called the non-atomic data accesses. So these are the traditional accesses which are not thread safe. And on the other hand, you have the atomic data accesses. So here, if you look within atomic data accesses, of course, these are thread safe. And here you have this range of, very relaxed, which are highly performant and barely synchronizable kind of models, and all the way down to sequential consistency, which are highly synchronizable, but performance they're very expensive. Now, what you see in between both of this is release acquire. So release acquire, let's say, balances both of these very nicely. So it is very, very highly performant. At the same time, it does offer some very interesting synchronizing patterns, like, for example, message passing. So, in a nutshell, just let's call release acquire to be take C11. And if you consider all the reads to be acquire reads and all the writes to be release writes, and atomic read writes or updates as they're called should be acquire and release. Okay, so this is release acquire in like one line. So just to get some intuition about how release acquire differs from sequential consistency, let's look at some standard examples. So I have two programs here. One is called store buffer and the other is message passing. Both of them are like very well-known examples. So let's look at store buffer first. So I have two processes and the shared variables are x and y. To begin, I'm going to assume that the values of x and y are both 0. Now process 1 is writing 1 to x and it is reading from y into a local register ry. And process 2 is writing 1 to y and it is reading from x into its local register rx. So the question is it possible that I can read both Rx and Ry to be 0? So obviously, if you think in terms of sequential consistency, this is not possible because the moment I write X and Y to be 1, of course, when I read them, I'm going to get 1, right? I'll not get both to be equal to 0. This is true for sequential consistency. Now, however, if you look at an execution under the release acquire semantics, as you see in the second process, I basically swapped the read and write statements because they pertain to different shared variables. Okay. Now, since this is allowed under release acquire, in my execution, I can now first begin by reading 0 from x, then I'll write 1 into x by process 1. Then when I continue, I can now read 0 into y and then write 1 into y. Okay, so essentially, under release acquire, I am able to obtain a situation where I can read both 0 into x and y. Now, to formally speak about this, so you see this execution graph here. So the intuition here is that I will speak about the execution graph in a bit, but right now, this execution graph has the usual relations of program order, right, per process. Now the reads from relation connects the writes and the reads, and you have the modification order. So if you look at process 2, somehow the read of x has not really realized that process 1 is written 1 to x, right? So the problem is that there is no path from the write of x1 to the read x0, which is why the read x0 is allowed according to this. Now, if you look at message passing, the second example I had, so here again, you have two processes. The first process is writing to both x and y, and the second process is just waiting until the y is changing from 0 to 2, and the moment that happens, it is reading from x. So if we observe this example, what we realize is that you do not see any weak behaviors. And the reasoning for that is as follows. So first of all, if you look at process 1, it has only two write statements. So there is no way I'm going to reorder them because release acquire does not support reordering of writes. Likewise, if you look at process 2, there is no reordering of reads possible. And also now, if you really think about it, process 2, when it is reading X, it is actually aware of the fact that 1 was written to X. So why is that so? So notice that to read X, first I have to, ensure that Y is 2. Now, because of the causality, now release acquire is like causal consistency. So when process 2 becomes aware that Y is 2, it also causally becomes aware that X was 1. And because of that, it cannot read value 0. All right, so this has no weak behaviors. So again, if you look at the execution graph for this particular example, so you realize that now because of the program order and reads from, there is a path that happens before relation, which makes process 2 aware that there was a write of 1 into x. So there is a path from write x1 to the read of x, which is why you cannot obtain, according to this, a read of x0. So now the declarative semantics for release acquire is given in terms of these execution graphs. So to get a consistent execution under release acquire, we need to be able to provide two relations. The first one is the reads from relation, which is basically mapping reads to corresponding writes in such a manner that the happens before relation, which is the transitive closure of the program order and reads from, is irreflexive. That is the first thing. Now, the second thing, I should also be able to provide a modification order, which is a total order on all writes to the same location, so that the happens before and the modification order do not contradict each other. That is the first condition. Secondly, I am not supposed to read overwritten writes. So if you now think of the message passing example, that's exactly what happened. The reason why I did not read x is equal to 0 is because it was an overwritten write. And lastly, if you think of the atomic read write, again here, when you have an atomic read write, you must always read from the latest write according to the modification order. Okay, so these are the three conditions, and the declarative semantics is now very simple given in terms of execution graphs respecting these conditions. So now, before I go into the further technicalities, this is just a summary for release acquire having so many nice properties. So release acquire has a verified compilation scheme to both PSO and Power. If you want to analyze programs under release acquire, you have some very nice program logics like RSL, GPS, Opera. It does support the intended optimizations by allowing you to reorder writes and reads when they are pertaining to different variables. So as we saw already in the example, if I have a write X followed by a read Y, it allows me to do the read Y followed by the write X. And for the optimizations, which sequential consistency does not support, there is a very intuitive semantics, both declarative and operational. What I'm going to talk next will be the operational semantics. And it is also known that these two are equivalent. The declarative semantics, given in terms of execution graphs, and the operational semantics, which I'll talk about, it is known that these two are equivalent. And lastly, one of the very nice things is that, okay, even if you do not know anything about release acquire, if you take a program and if you know that there are no data races equal to sequential consistency, then automatically it is also known that you will not get any weak behaviors according to release acquire. Now, note that this is not something which is true for the full C11 model, but it's true only for the release acquire fragment. So, even before I go ahead, the summary at this point of time is that release acquire is a well behaved fragment of C11, and therefore there are a lot of papers recently which have studied many interesting questions about release acquire, and this talk is basically trying to talk about one such question which pertains to the reachability problem of programs which run under release acquire. So even before I go to the reachability problem, I'm first going to talk about the operational model for release acquire. All right, so this is like a high level description of the operational semantics. So if you think of release acquire, so in this particular slide, I am having two processes, P1, P2. In general, you can have some n number of processes. So the memory is basically a collection of messages or views, as you may want to call it. So it's like a memory message pool. Now, every message you see in this memory pool is obtained when a write operation is done. So for example, right, if you take this, the message where x is 1, that 1 represents the value that was returned to x. Now, below that, you see two numbers, 4 and 1. What are these? So, these represent the logical clocks for the variables x and y, assuming I have just two variables x and y. So, in general, if I have k variables, a message would contain, okay, if there was a write which was done to a particular variable x, the message contains the value of x along with the logical clocks for all the variables, right? So, this is how a message looks like. So now let's understand what a configuration looks like for a process in release acquire. So every process maintains what is called a local view. Now, what is a local view? A local view is nothing but, again, a vector clock, one per variable, which is maintained by each process independently and separately. So in this example, I have three instructions, and assume that the local view for x has timestamp 3 and the local view for y has timestamp 2. I have only two variables, x and y. A and b are my local variables or local registers. So let's understand what happens when I try to do a read instruction. So the first one, I'm trying to read the value of x into a local variable called a. So this is how I proceed. Okay, so first I'm supposed to select a view from the memory such that it pertains to x, right? Because I'm trying to read from x. So first of all, I'm just going to ignore all the messages from the memory pool which do not pertain to x. So now I have two messages in the memory pool corresponding to x. Now what am I supposed to do? So I look at my local view. My local view for x is that the timestamp is 3 for x. So if I want to read from the memory pool, I can read from a message where the timestamp for x is at least equal to 3. So if I look at the two messages available for me, one of them is obsolete because the timestamp for x is 1, where the value is 3. So what is applicable is just one message where the timestamp for x is 4 and the value is 1. So that is the message I'm supposed to read from. And that is what I pick. And once I choose the message that I'm supposed to be reading, I have to update my local view. So how do I update my local view? I take my current local view and I take the timestamps in the message in the memory pool. I do a merge operation, which is basically a component wise max. When I do that, the new local view is updated to 4 and 2, and the value of a now becomes 1 because I've now officially read the value of x from the memory pool. All right. So now we can proceed to how do you write an instruction? What happens when a write instruction happens to the memory pool? So when you write a value, so here I'm writing 2 into the variable x. So whenever a write operation happens, I'm going to add a new message to the memory pool. So the first thing I'm supposed to do is I have to create a new local view, right? Because the point is when I add a message to the memory pool, I'm going to add a value to x. I'm going to add a sequence of timestamps corresponding to each variable, which is of course coming from my current local view. So the current local view says that the timestamp for x is 4, timestamp for y is 2. Now, since I'm going to write a new message, I have to pick a higher timestamp for x, which is higher than my current local view for x, and it must be a fresh timestamp, which means that I should not have that timestamp I'm going to pick already present in the memory. Okay, so for example, here it is 4, so higher value could be 5. And notice that if I look at my memory pool, I do not have the timestamp 5 for any messages of x. Okay, so 5 2 is perfectly fine. Now, once I do that, I update my local view to say that, well, now my new local view is 5 and 2 respectively, and I'm going to add this new message to the memory. So the message here is that every time you encounter a write operation, your memory pool or message pool is continuously growing larger and larger and larger. So potentially you're going to have an infinite size message pool as part of resupply. Now, once that is done, the last instruction here is a read operation from y. So this we have already seen for x. So it is similar. Now my local view, according to my local view, the timestamp for y is 2. So I'm going to look at messages from the memory pool whose timestamp for y is greater than 2. So here I can pick the value of 5 for y because the timestamp is 7. So I pick the value, I do the merge, and I'm done. So the last instruction I have to talk about is the atomic read write, which is basically doing a read followed by a write in an atomic manner. So let's see how that is done. So, okay, I have a write to y. So I've added new message to the memory pool. This is same as what we saw before. Now, when I have the atomic read write, this is what I do. So the first thing is I am supposed to first pick a message from the memory pool such that the value for x coincides with the value of the register R. Okay, so here the value of the register R is 1. So I'm supposed to pick a message from the memory pool where x is equal to 1. So I do have such a message. And it is indeed readable because the timestamp is 3 in the memory pool. My local view timestamp was 0 and 3 is larger. Therefore, I can pick that message. So I've now read it. Now I have to atomically write, which means I have to now add a new message to the memory pool. And now here's the thing, okay? So to ensure the atomicity, the message that I add to the memory pool, the timestamp I'm going to choose for X is going to be exactly one more than what I have just read. Okay, so basically what that means is that the new message I add, the X timestamp is going to be 4, which is exactly one more than that. Now, this also conveys an important message that if you have an atomic read write, and if you are choosing a message from the memory pool to read from, obviously you cannot choose the same message to read from for another atomic read write. The reason is simple because if I choose this message once to read from as part of an atomic read write, the moment I add a new message to the memory pool, the timestamp is going to be one more than what the original message had, right? And we already know that whenever I make a write, any message I add to the memory pool should have a fresh timestamp. So this is why it is actually going to be an atomic read write, that there is nothing coming in between this read and the write. Okay, so this operation is also known as compare and swap and read modify write, depending on how we want to call it. So I guess I'll be calling it atomic read write or CAS, depending on which context I'm talking about. So now that we have seen the three kinds of instructions, read, write, and atomic read write, let's look at a sample execution under release acquire, keeping this operational semantics in mind. So here's again a simple program having two processes, and initially the register values are 0. And the question I want to ask is it possible to reach a configuration where register 1 has value 0, register 2 has value 1, and register 3 has value 2? Okay, this is what I want to understand. So let's see. So again, notice that the two processes initially have local view 0 and 0 respectively. The message pool has two messages which represent the initial values of x and y, right? So x is 0 and y is 0 to begin with timestamp 0 and 0 respectively. So process 1 starts executing. So I was supposed to read from x into register R1. So since x, the only possible message to read from was just having value 0, I am just reading 0 into R1. I continue, I'm going to write y equal to 1, which means I added to the memory pool the message y is 1 with timestamp 0 and 2. So I've just chosen 2 as a timestamp for y. The new timestamp for y is 2. So that's a new message added. So now I'm going to process 2. Here I'm supposed to read from x. So I could have read either of the two values. Sorry, I was supposed to read from y, I guess. Yes, I was supposed to read from y. So here notice that the local view of process 2 has timestamp 0 and 0. So which means that I could have read either from the message where the value of y is 0, or I can read from the message of y where the value is 1. So I'm just choosing to read from the one where the value of y is equal to 1. So that means that R2 is now equal to 1. Now I have a write operation on x, which means I add a new message to the memory pool, choosing the timestamp of x to be 1. And now I have another write operation. Here the timestamp chosen is 3. So now I come back to process 1. Now when I come back to process 1, I'm supposed to read the value of x into the register R3. So now notice that the local view according to process 1, according to that, the timestamp for x is 0, which means that the potential candidates I have in my message pool to read from x are basically I can either read the value of x is equal to 0 because timestamp is 0 and 0. It matches with my local view for x, or I can read x is equal to 1, which has a timestamp 1 in the message pool higher than my local view, or I can read x is 2 from the message pool whose timestamp is 3 higher than my local view, right? So it's a non-deterministic choice. So here the process has chosen to read from the message where the timestamp was 3, which means the register R3 has got the value 2. So this execution indeed agrees with the question that I can indeed reach a configuration where register values R1 was 0, R2 is 1, and R3 is 2. So now I guess we have all the technical background necessary regarding the operational semantics of release acquire. I think we are now in a position to talk about the reachability problem under RA. So I have roughly two parts. The first part is non-parameterized reachability, which means that I have a concurrent program with a finite number of processes given to me. And the question is, okay, of course, it is running under release acquire, and the question is, can I reach a certain configuration? So this paper appeared in PLDI 2019. It's joint work with Parosh Abdullah and Fauzia Atiq from Uppsala University, and Jatin Arora, who was an undergraduate student at IIT Bombay. The second part of the talk, I will touch upon parameterized reachability when the number of processes are going to be unbound. Okay. So, formally stating the reachability problem, the question is that I'm given a program P and I'm given a state S. So, the state S basically is the control along with the memory. So, the control basically tells me the program counter where I am in the particular process or in all the processes, along with a particular configuration of the memory. Okay, this is the question. Now, we all know that typically state reachability is same as safety, right? Because I may want to avoid reaching a certain configuration and I can state it is a reachability problem. So the question is a certain control or memory status reachable in a given program which runs under release acquire? And what is the decidability of this question and what is the complexity of this question? That this is what we want to answer. So, okay, at the time when we worked on this question, the reachability was open for release acquire, and we sort of settled it by showing undecidability. So that's the first thing I'll be talking about. But if I ask the same question under sequential consistency, then we know the answer, right? Because it is already known that under sequential consistency, the reachability problem is piece complete. Now, indeed, in our case, every process is a finite state process. So it's a finite state object. And the question is, under the situation where every process is a finite state object, what is the complexity of the reachability problem and what's the status of decidability? So one thing to notice here is that it does not matter if I know the result under sequential consistency or not, because anyway, I cannot borrow the results from sequential consistency to release acquire because the semantics is different. As we already noticed, release acquire is allowing some reorderings, which was not the case under sequential consistency, which is why we need a fresh look into the problem. Even though the problem seems to be the same kind of question, I cannot borrow the techniques. So this is the first result that the state reachability problem is undecidable for release acquire. So I'm not going to talk about all the details, but I'll just touch upon the key elements of the idea behind undecidability. So the way we prove this result is by reduction from what is called a post correspondence problem, PCP in short. So I'll first describe what a post correspondence problem is. So an instance of the post correspondence problem is presented as follows. So you're given two lists, U and V. So here you see I have a list called U, I have a list called V. Now both the lists have equal length. And what does a list look like? A list is basically a sequence of words over some alphabet. So in my case, U and V both have length 4. They both contain words over an alphabet AB. And the question is that can you find a subset, a sequence of indices from your whatever 1 to n, if n is the length of your list, so that when you concatenate together the words in the list U in the indices you have chosen, and when you also concatenate the words at position, the same positions in the list V, do they give you the same word? Okay, so in this example, for instance, if I look at the indices 2 followed by 1 followed by 4, so 2, 1, 4 happens to be my solution because you look at the words you obtain when you put together the words at positions 2, 1, and 4 in the list 2. The word you get is A, B, B, A, B, B. That is the word I get from list 2. And if I look at the same positions in list V, you can see that I am getting the same word, right? So I get A at position 2, then followed by BB, and the remaining would be the same, right? So basically, I get the same word across both the lists. So this is a solution for PCP. So our idea is to say that, okay, you start from an instance of a PCP, and can you construct a concurrent program with some finite number of processes which runs under release acquired, so that you can say that whenever there is a solution for the PCP instance, I will be able to reach, let's say, the terminal states. So I'm assuming that every process, I have a particular program counter called term, which is what I will reach at the end of executing all the instructions of a given process. So the reduction is that there is a solution for my given instance of PCP if and only if I can reach the terminal instruction in all the processes under release acquire in my constructed program. So the job is to somehow construct a program and to say that this reduction is polytype. Okay, so let's see the intuition behind that. So our reduction is such that the program we construct is just having four processes, P1, P2, P3, and P4. And the idea is that P1 is going to take the list to the first list, and it is going to guess a sequence of indices and a sequence of letters coming from those indices. Okay, so when I say guess, I'm just going to write down to some variables the letters at those positions as well as the indices I've seen. Now, independently, process P2 does the same thing on the second list view. Okay, so it's like P1 thinks that from the list view, this is the solution. P2 thinks that from the list view, this is the solution. Now, P3 and P4 are supposed to be verifying whether these two people have thought the same thing. So P3 is supposed to, let's say, read the indices of P1 and the indices of P2 and check that, they are the same set of indices, same sequence of indices. And P4 is supposed to check the sequence of letters written by P1 and P2 and ensure that the letters are the same. Okay. So it's like two people write and two people read and ensure that it's indeed a viable solution. It's a valid solution if indeed the original instance had a solution. Okay, so it sounds easy. Let's look a bit into the complications possible and how we can work around it. So I've replaced letters with these colored beads here. So here is I have a similar looking example. I have two lists called A and B here. Again, I have four entries respectively. So we can form words out of these color beads. So process P1 is going to work with two variables, x1, x2, when it wants to copy the letters, and it's going to work with two variables, y1, y2, when it wants to copy the indices. Okay, so let's see what P1 does. So P1 has decided to read the first entry of the list A, which means it is reading into x1, x2, and x1 alternately, the symbols of the first entry from the first list. When it finishes reading the first entry, it writes the index 1 into the variable y1. Then it continues guessing it. So now it is thinking that maybe it should read the second entry. The second entry again has whatever red, blue, and blue, and it reads 2 into y2. And then finally it decides to read the last being the entry 3. And just a moment. Yeah, sorry. So because of keynote, it's going to delay again. All right. Okay, so what process one has done so far is it has read, it has basically written into x1, x2 alternately the letters it has chosen to read. And whenever it finishes reading a particular word, it is writing the corresponding index into variables y1, y2 alternately. Okay, that is what process P1 has done. And it thinks that it is a solution. Now we know it is not a solution, of course, because if you just put together the words in the list A in these positions 1, 2, and 3, if you look at the same word you will obtain in the list B, you will realize that the words are not the same. Okay. Now P2 in this case, let's say guesses the same sequence. So if you look at the list B, so P2 is going to take from list B. So P2 is going to use variables x3 and x4 for writing the letters of the list. So it looks at list B. It takes the first entry, it has green and blue. So it writes green and blue respectively to x3, x4. Then it writes 1 into the variable y3. Then it continues with guessing the next one to be the entry 2. So it writes blue, red, green, red, and blue, and it writes 2 into y4. And it chooses its last one to be the third entry in B, which has blue, blue, green, and red, and it writes y3 to be 3. Okay, so P1, P2 have done their job, they're done. So now let's see how P4 is supposed to verify and conclude that this is not a correct solution. Okay, but here, okay, let's see if P4 does the following, if it is allowed under release acquire. So P4, let's say, reads off the first written values of x1, x3, which happen to be green and green, which are matching. It proceeds to the next one, it reads blue and blue, which are matching. Okay, then it is going to read the next green and green. Okay, and it reads red and red, blue and blue. It jumps some values. Okay, and then it reads the last red and red. Now notice that when P4 is reading, P4 is reading increasing timestamps, right? Because every time a write was made by P1, there was a timestamp corresponding to X1, there was a timestamp corresponding to X2. So whenever P4 reads, remember, P4 had a local view. And whenever P4 makes a new read, it is supposed to read from a higher timestamp, which is following that. It so happens that P4 conveniently chose a subsequence from the actual sequence, and it is going to conclude that this is a solution, which is unfortunately not true. Okay. Now, just to get a peek into what this really means in terms of release acquire. So I'm assuming that P1 to T7 are the timestamps that P1 chose when it has written into X1, X2. And T1 prime to T7 prime are the timestamps chosen by P2 when it wrote to X3 and X4 respectively. So of course, T1 to T7 are in increasing order. Likewise, T1 prime to T7 prime are in strictly increasing order. Now when P4 begins, initially its local view for X1, X2, X3, X4 are all zeros, right? Now let's see. So when P1 reads from X1 and then it reads from X3, its local view gets updated to T1 0, T1 prime 0. Notice that T1 was the timestamp of X1 according to P1. T1 prime was the timestamp of X3 according to P2. And now P4 has not read an X2 or an X4, so it retains the initial timestamp of 0 and 0. All right. Now let's say that P4 reads actually the next written value by P1 and P2 respectively. So the timestamps now become T1, T2, T1 prime, P2 prime. Very good. Now let's say that P4 jumps a bit because it realizes that the next values are not matching, so it doesn't want to read that. It is trying to cheat, in fact. Let's say it progresses and reads a blue and blue, which are actually the same value. When it does that, let's see what happens. So notice that when it reads X2 and X4 respectively, the timestamps of X2 and X4 get upgraded to T4, T4 prime because that were the written timestamps. But also notice that because of the causality, the timestamps for X1 and X3 will also change. This is because when you write into the memory pool, so when P1 wrote the value of X2 with the blue beat with timestamp T4, when it puts this into the memory pool, its local view for X1 would be T3, right? Because it has written, into X1 before with the timestamp T3. So when P4 reads, it inherits the previous timestamp of X1 and respectively X3. Therefore, you will also see, it will inherit the values of, it will inherit the values of X2 and X4, right? Because I have currently read from X2 and X4, it inherits X1 and X3. Yes, okay, fine. So this is what happens, right? This is what happens in release acquire. It's consistent with our definition of operational semantics. So now what we know is that this kind of reading is not going to work. If I want to ensure that P4 does not cheat, I need to do something more. So again, I'm jumping here and reading here. So again, here when I read X1 and X3, I get T7, T7 prime. But again, because I'm going to inherit T6 and T6 prime, the local view for P4 is T7, T6, T7 prime, T6 prime. Okay, so now we keep this in mind that whenever a process makes a read at a particular point, it will inherit the causally past timestamps written by the same process, depending on the local. So this is our fix. So rather than allowing P4 to read the way it did just now, again, I begin with all the local timestamp 0 for X1, X2, X3, X4. So I'm going to assume that the initial value for X1, X2, X3, and X4 is some black beat. Okay, this is my initial value. I usually say 0, but because I've chosen here, to represent with beats, my initial value, let's say for X1, X2, X3, X4 is a black beat. So here is how I begin. So P4 is going to do an atomic read, right? So it's reading from the first process. It's not a simple read. That's the only difference. Okay, it's doing atomic read, right, from X1. Now it is realized that it's reading green. So when it is reading green, what happens is that, of course, its local view gets updated to T1. The others do not change. But it's an atomic read write. Remember, an atomic read write is a read followed immediately by a write. So here I am reading the green and writing black. Okay. So when I write black, the timestamp of X1 now becomes T1 plus 1 because that is semantics visited. It is atomic. Now, after it does that, it is trying to read into X2 the black beat. Now, this is possible because the current timestamp, according to the local view of X2 is 0, it can read from the initial X2 equal to black beat. Okay, so this is possible. Now, remember, it has to verify, according to the second process, whether X3 also has a green beat. So it is doing an atomic read write with respect to X3 of green, and it's again writing black. So now its local view was already T1 plus 1, 0, 0, 0. Now because T1 prime was the timestamp when X3 wrote green beat, the local view gets updated to T1 plus 1, 0, T1 prime and 0. Now there is a write part after the atomic read where I'm writing black beat into X3 with the timestamp T1 prime plus 1. Okay, so far so good. Now let's say that it tries to read the black beat into X4. It is possible because the initial write of the black beat into X4 is readable here because the local view from X4 is readable. Now let's say it proceeds without cheating as yet. So it is reading the next return value by P1 without jumping. So the next return value was a red beat with the timestamp T2. So the local view gets increased. And there is a write of the atomic read write where it writes the black beat into X2 with the timestamp T2 plus 1. Okay, so far so good. And now when it tries to read the black beat into X1, it cannot read from the initial return black beat. It has to read from, as you saw just now, sorry. It is going to go back all the way. I'm sorry about this. I think it should let me know that if I want to go back, it goes all the way. Okay. Yes. So what I wanted to say was that this read of X1 comes from the first atomic read that was made into X1. Likewise, in process 2, it is doing an atomic read write of X4. It has read the red beat. It is matching the red beat and it's writing the black beat into X4. And it is trying to read the black beat from X3. It is possible from the previous one because the timestamps match. Notice that the previous time a black beat was written to X3, the timestamp was T1 prime plus 1. The current local view for X3 is same T1 prime plus 1. Now let's say it jumps. Okay. Now when P4 jumps as it did before, it's trying to cheat. Now when it tries to cheat, it's doing an atomic read write again. So it's reading the blue beat and it's writing the black beat into X2. So here is how the timestamps look like. So notice that the timestamp of X2 was T6. It has inherited T5 as the timestamp for X1 as we saw before. And now the next, according to this sequence, if you observe, I am trying to read the black beat into X1. Okay. The question is, will it now work? Now notice that the timestamp of X1 according to my current local view for P4 is T5. In order to read a black beat, when was the last written black beat according to what I have in my message pool? It was written by the last atomic read write, which happened at timestamp T1 plus 1. Now T5 is strictly larger than T1 plus 1, which means that at this point of time, P4 will get stuck. Okay, so this atomic read write has kind of ensured that P4 cannot jump. And the process P4 now has no choice but to read exactly in the same order in which P1 has written, read exactly the same order in which P2 has written, which means that if there was a mismatch in the solution, P4 should be able to catch it. And indeed, if there's no mismatch, then of course it will continue verifying. And when it finishes it, it will say that it's a perfect match. And P3 does exactly the same thing by verifying that the indices are the same. Okay, so this is the solution by encoding the post correspondence problem. Now, it is not a good news because somehow we are saying that verification under release acquired is undecidable, which means the reachability is undecidable. So, what is a potential workaround, right? Can we still do something about this, even though the original problem is undecidable? So, the usual standard technique whenever a problem becomes undecidable with respect to concurrent program is that we have the tried and tested context bounded analysis. So, this is a very efficient under approximation technique, which is known for sequential consistency. And the idea here is that, okay, you have a concurrent program. Rather than look at all possible runs, I'm going to look at a subclass of runs where, let's say, when a process runs, it's a context. When I make a switch, when another process takes over, that's a context switch. And I keep going. So I'm going to analyze only those runs where the number of context switches is bounded above by some known constant. Okay, so this is clearly an under approximation. And this has been proved to be very useful in finding bugs in several benchmark examples. So just to give a better idea of what I mean by a context switch. So if you have two processes P1 and P2, the execution where P1, P2, P1, P2 strictly alternates is not bounded context because every time there is a switch from P1 to P2. However, if I look at the run where P1 runs and there is only P2 for the rest of the lifetime, it is a one context bounded run. So this is indeed an example of a context bounded run. Now, there are many tools which are useful for doing context-bounded analysis, like Chess, Corel, CSEC, etc. So, the natural question is, since this is a tried and tested technique under sequential consistency, can I do a context-bounded analysis under release acquire 2, and would that be a good under approximation? So, let's go back and look at our constructed program. So, if you remember, what we said was that P1 works first by giving its guesses, followed by P2. P2 and P1 and P2 both write their supposedly chosen solutions. P3 is going to read and verify whether the indices are same, and P4 then is going to read and verify if the letters are the same, which means that this execution is actually a context bounded execution, and I'm switching from P1 to P2, P2 to P3, P3 to P4, right? So it's basically a three context bounded switch. So which means that our undecidability actually works even for the subclass of context bounded analysis. Okay, so basically this means we can't use context bounded analysis either. So what do we do, right? We need a different kind of under approximation which is more suited for lace acquire. Now, that under approximation happens to be what we call a view switch. So, it's not a bounded context switch. We are going to call a bounded view switch. So, what is a view switch? Okay. So, let's look at this example and understand what a view switch means. So, here I have two processes, the red and the green. So, if you now look at what a view switch means, roughly speaking, a view switch basically is something that happens when a process makes a read from, let's say, the write written by another process, and when it makes that read, its local view is going to change. Okay, so when that happens, I say that there is a view switch. So in this example, when the green process reads a value 1 from y, there is a view switch because initially the local view for y was 0 for the green process, and when it reads a value 1 written by the first process, the timestamp is increased to whatever process one had chosen for y, so it's a view switch. Likewise, when the red process is going to read the value 2 into x, now this was written by the green process. So to begin with, the red process local timestamp for x was 0 because it had never written to x, whether the green process had written to x, so it would have chosen a higher timestamp. So when the red process reads the value 2 from the green process, the timestamp is increasing. So this is clearly a view switch again. Now, notice that when the red process reads the value 3 from y, which was also incidentally written by the green process, this is not a view switch. Why? Because, again, because of the causality, right? So, when the red process read the value 2 written by the green process, it has updated its local view both with respect to the timestamp of X and timestamp of Y, right? Because the green process first wrote Y and then wrote X. So clearly, in the message corresponding to X, it also inherited the timestamp of Y, which it had chosen earlier. As a result of which, when the red process has read the value of 2 from X, it has already inherited and changed its local view into that timestamp of Y chosen by the second process, the green process, which is why when the red process reads a value 3 from Y, it is not a view switch. Okay. So essentially, all that we are saying is that a view switch need not happen whenever there is a read from another process is right. A view switch happens only when the view changes as a result of your read. So in this example, how many times did the view change? It has changed 2 times. So it's a 2 bounded run. So now we are going to rephrase our under approximation to ask whether it is decidable to find if I can have reachability under a view switch bounded run. Okay. So here is my message pool once again. So if you look at the message pool, I have all the messages corresponding to all the writes made so far. But now I'm going to say that because I'm focusing on a run where the number of view switches are bounded by some constant, it's enough for me to consider a message pool where I only have the messages which are responsible for a view switch. Okay, so for example, if you look at this, we said that the write of y to be 1 was responsible for a view switch. So that is important. So I keep that in my memory pool. Likewise, the write of x to be 2 was again responsible for a view switch. So I'll keep that message when x is equal to 2, but others are potentially useless. Okay. So I'm going to call a message to be an essential message. Why did? It is responsible for a view switch. So here I'm kind of shading out the messages which are not necessary for a view switch. Now, by doing so, I can actually reduce the size of my memory pool. And if I know that I'm focusing only on runs which are, of bounded view switch, it also results in having a memory pool where the number of essential messages are also bounded above by a constant. So, in other words, if I focus on view switch bounded runs, I can also, work with the memory pool where the number of messages are also finite or bounded above by a same constant. Okay, because now the idea is that I am going to keep in my memory pool only essential messages. What is an essential message? An essential message is a message which was obtained to me because it was helping me with the view switch, right? So here, as I said, the write of y1 resulted in an essential message. The write of x2 also resulted in an essential message. The other writes are not essential messages because they are not responsible in a view switch. Okay, so in some sense, it makes the problem tractable because the size of the memory pool goes from infinite to somehow finite and bounded above a constant. So a natural question that arises is, in the undecidability proof that we saw, did we require an unbounded number of view switches? Okay, this is a question we need to answer, right? Because obviously, if we are going to claim a decidability with bounded view switch, it better be the case that the undecidability result required an unbounded view switch, right? Which is actually true. Because if you now kind of rewind and think of the undecidability, whenever the process 3 and 4 were reading, okay, from the earlier process P1 and P2, every time there was a new read, the view was actually changing, right? Because it is going in strictly increasing timestamps. And somehow there is a loop inside P1 and P2, right? Because it's like keeping on guessing a potential solution to PCP. So it's a loop. So whenever you have a program where there is a read happening in a loop, the number of view switches is going to be potentially unbounded, even though the number of context switches need not be unbounded, right? So it may be the same process which is running. So there is no context switch, but this process may be reading from a loop written by another process where the views are constantly changing. So that leads us to our under approximate problem, which we call k bounded reachability problem, where the reachability problem is restricted to k bounded runs. So the result we have is that if I restrict myself to the view switch bounded reachability problem under release acquire, then I can reduce it to the classical bounded context reachability problem under sequential consistency. And what we do is we give a code to code translation, which means I have the release acquire program. I fix a view bound switch. And then if that view switch bound is k, I know that I can convert it into an equivalent problem under sequential consistency, where the number of context switches is k plus n, where n is the number of processes. Okay, so intuitively, if you think about it, why is this true? So if indeed k is the number of view switches I'm going to observe, this is what I'll do. Okay, first I will. So also, okay, before I continue how I do it, remember that an essential message is a message that came from a write responsible in a view switch. Okay, so this is what we can do. If k is my bound for the number of view switches, I will first guess which are the processes which are going to result in a write, which is going to result in a view switch, which means these are the processes which are giving me the essential messages. So I can guess these, I can run them in order. Okay, so I'll run the process giving me the first essential message. Then I'll run the second process giving me the second essential message. And I keep doing until I finish all the essential messages needed, which means that when I finish running these K processes potentially, I've got potentially K context bound switches. Now I'm also saying that every message I require for a potential view switch I have already generated, which means that whatever messages are going to be generated in the future are useless. And now, since I've got all the necessary messages responsible for the K potential view switches, I just need to run the remaining processes in order. Okay, so now I can run process one, process two, extra process n, all the n process to completion. And this can result in n extra context bound switches. So this is why from a K view switch under release acquire, I can come to a K plus n context bounded switch under sequential consistency. So, as a corollary of this theorem, what we can also say is that the K bounded reachability problem under release acquire is decidable for finite state programs. So, of course, I'll touch upon an intuition of what I just said, verbally. So, this is the same program that we had. So, remember that the view switches we needed were two, right? Because there was one useful write coming from the first from the first process and another from the second process, right? So, I just need to generate those two essential views. So what we can do is I'll first guess that the write of one is going to result in an essential message, which will help me in a view switch. So once I make that guess, I can run the first process independently, and I will now record this message as an essential message. Okay. So and then what do I do? The second process starts running. The starting point is going to be this essential message it is generated, and the second process runs independently, it generates the second essential message, and then the first process continues from that point, from this essential message, and continues till I've completed. Okay, so this is the rough picture. And now these positions, okay, where these essential messages are generated are what are called interfaces, because I have to now thread together these interfaces, stitch together these interfaces, so that I have a seamless run under sequential consistency, where I have to now verify that my guesses were indeed correct. Okay, so for instance, what I've done so far is that I've simulated the first process under sequential consistency independently, and I generated the essential message. Then I've done the same thing for the second process. And now what remains is I have to validate that these essential messages I've guessed are indeed correct, which means that if this was an essential message generated first, the second process can actually begin from that point, continue. And if indeed the second message was generated by process two, from there I can continue again with the first process and so on and so forth. Okay, so of course to do this, we had to add some extra local and global data structures, which is basically maintaining the local views of all the processes. The data domain did not change. The number of variables we used did not change from the original program to the translated program. We just had to maintain data structures which should simulate the message pool, which is now bounded by K, as well as the views of the local views of each of the processes, right? So essentially, that's pretty much what we had to do in order to obtain the sequential consistency code from the original program. And then we implemented this as a model checker. So we call the tool view bounded model checker. So the input is the concurrent program along with the bound K that we are supposed to check. And then we do the code to code translation, getting a program at a sequential consistency, which is given to the standard CBMC checker. And the CBMC checker will answer the question whether a certain assertion is reachable or not. So we indeed verified the results of this with standard litmus test just to ensure that our translation is correct. And what we observed was the following. So whenever we could find a bug, we realized that the number of views bounded switches were maximum 5 that we required. Also, we compared it with the classical stateless model checking tools like Tracer, RCMC, CDS checker. Now, indeed, these two techniques are quite orthogonal to each other, right? Because in some sense, the SMC tools do an exhaustive analysis of the entire state space. They are not tailor-made to find a particular bug. They are not reachability tools, whereas VBMC is tailor-made to find a particular bug. So when we took safe programs where it is known that there are no errors, obviously, the SMC tools were much better than VBMC. And then we did some we basically took a program, and then we fenced some of the threads, which means that they are like sequential consistency, and the bug was isolated to some particular thread, which means that the probability of finding a bug across all executions was very small. Okay, when we kind of put the bug in a certain position only in one particular thread, then VBMC was much faster, because the thread was just isolated to the error was isolated to just one position, whereas the SMC tools were still doing a exhaustive checking of all the traces, and they were taking more time. So the message basically coming out of this is that these two are orthogonal techniques. You cannot just say that one is better than the other. VBMC is targeted to reachability, whereas SMC tools do an exhaustive analysis of all the traces, right? So that brings me to the end of the first part where I was talking about non-parameterized reachability, which means we had some fixed number of processes under release acquired. And now I'm going to the second part where I'm going to talk about parameterized reachability in release acquired. So in
Krishna,
parameterized,
I'm afraid we need to wrap up soon because we are on the schedule. So
can
yeah,
I have 4 minutes?
sure.
Okay, yeah, I won't take more than that. I'm like almost done also, because here I'm just going to give an high level overview of parameterized reachability without going to the proof techniques. Okay, so the question is that how does parameterized reachability look like? And what I'm going to talk about, one part of that is published work in POTC 22. This is joint work with Roland Mayer. Advait was a graduate student here, as well as Soham Chakrabarti from TU Delft. And the full set of results was published earlier. It is still available as a technical report in archive. Okay, so let's see the setting. So to begin with, I'm going to consider a setting where what do I have? I have unbounded number of processes. They are all identical to each other, and I do not have atomic read-write or CAS operations. Now, this may look restrictive. Why am I not allowing CAS operations? So the answer to that is, if you allow CAS operations, even when your respective processor do not have loops, we can simulate the undecidability result of PLDA 19. In some sense, what I'm saying is that you take a non-parameterized program where the threads are distinguished, where you have compare and swap or atomic read write. You can reduce it to the setting where you have unbounded number of threads, even though they are acyclic. Even if you allow CAS operations, you get undecidability here, which is why I'm going to focus on parameterized reachability to begin with without CAS operations. Okay. The first thing that I want to say is that what is the advantage of doing this, right? So apart from a theoretical perspective, we get a simplified semantics under release acquire, and I'll just give the intuition why the semantics is simplified. So here, I have like identical process. There are clones of each other somehow. So let's say the first process generates the message x1 at the timestamp t. Then another clone can generate the same message with a higher timestamp. Yet another clone can do it the still higher timestamp, and so on and so forth, right? Because they are all the same identical program. So basically, what this means is that if a particular x1, if a particular variable and a value can be read, it can be read any number of times, because there is an infinite supply property. Somehow, in literature, it's called the copycat lemma. So this is the copycat lemma for release acquire, if you would like to put it that way. Now, this allows us to say that I do not need to compare timestamps, which was a big problem earlier, right? A lot of the operational semantics earlier required me to compare timestamps. Here, I'm saying that just forget about it, because you anyway have enough number of them, and this allows me to abstract my timestamps. Okay, so now let's look at a slightly more interesting setting where I just not have an unbounded number of identical threads, but I also have a bounded number of distinguished threads which have the compare and swap operation, but which do not have loops. Okay, suppose I have this setting now. So under this setting, it's still okay not to maintain the timestamps for the unbounded part which are identical, as long as I know the relative ordering of the writes here, and how they are placed with respect to the writes and distinguished threads. So which means that I'm going to work with an abstract timestamp where, as far as I'm concerned about the identical threads, I don't maintain the exact timestamps. I just maintain the ordering of them with respect to the distinguished ones. And the distinguished timestamps, I keep them as they are. So now notice here that in this setting, the number of distinguished threads are bounded by some number, which means, and they have no loops, which means that I get only a finite number of timestamps from the distinguished part, and I do not have to maintain explicit timestamp for the identical part, which means that I can get away by only having a polynomial number of timestamps as many as the number coming from the distinguished number of threads. So the result is that we can show the reachability problem here is p-space complete by encoding this into a Horn clause problem. And this in turn can be encoded as a query evaluation question in a particular class of data log called linear data log, for which the query evaluation is known to be p-space complete. The p-space hardness comes from QBF SAT. So now we are more ambitious and we want to ask what will happen if I add one unrestricted thread. Okay, so apart from the setting I had before, if I have an unrestricted thread, the problem becomes NXP time complete. And now if I add one more thread to it, okay, even though it has no cas, we do not know the decidability status. We just know that it is non-primitive recursive. In fact, I just want to point out here that even if I have just two threads, okay, which do not have cas operation, but which can have loops, it is already non-primitive recursive and the decidability is open. Okay, which means that, remember, my undecidability result had atomic read, right? Now I'm saying if you remove the atomic read, right, from the PLDI 19 undecidability, we do not know the status of undecidability. We just know it is non-primitive recursive. So this is an open question, which also has implications in the parameterized setting, and I'm done. Thank you so much for your attention.
Thank you so much for a very nice talk. Before we get talking, I think we have time for, let's say, one critical question.
I have a question, well, it's critical.
Well, please go ahead. Yes, go ahead.
So, thank you for the nice talk, and thank you for going through the details of the proof. That was really nice. So if what happens if you just take away cas completely? Is things decidable in the unbound case? So that will you cover that with your variations.
Sorry, can you repeat?
So you still have loops, but you don't have any cases. Is this decidable?
Okay. So you have loops, but you do not have any cas operations.
Yes.
Okay. So you're saying in the I see. Okay. So yes, this would be decidable. Yes. This should.
This is decidable.
Yeah.
Okay. And what if you have probability and cas? So kind of so it's not unbounded, but you can have an arbitrarily large terminating trace.
Okay. So you want to have an arbitrary large number of.
Probabilistic choice. So does this give
Aha. That's a very interesting question. So you basically want to consider probabilistically square.
Yeah.
Well, I would say that's part of future work because I am not aware of probabilistic release acquire. I know probabilistic TSO is there, but perhaps not release acquire.
Okay.
Maybe my gut feel is to say that maybe you can get back decidability, perhaps. But no, I wouldn't think so. Actually, wait. I think that you would be able to reduce the probabilistic setting to the non-probabilistic one where you do have the undecidability.
Right. Satisfied?
I'm satisfied. Thanks. Sorry.
All right. Thanks again, Krishna, for coming and giving a very nice talk.